Today on Quickly Quantum, Quantinuum just put one of its most accurate quantum computers inside an Oracle data center, right alongside Oracle's own AI server racks. So, is that the moment quantum computing turns into real infrastructure? Or is it still just a very expensive appliance waiting for a use case? Before that, in the headlines, a new Nature paper pushes silicon spin qubits a step closer to real error correction. South Korea names quantum one of 7 industries it's betting the next decade on. D-Wave picks up fresh government funding in Canada. And a university in Seoul is about to install IBM's newest processor. Welcome back to Quickly Quantum, your daily brief on the quantum frontier. It's Thursday, August 13, 2026. Let's get into it. First up, out of the Netherlands, a new peer-reviewed paper in Nature from Lieven van der Sijpen's group at TU Delft just demonstrated something called wait-for parity checks on a silicon spin qubit chip. And if that phrase means nothing to you, stick with me for one sentence. A parity check is basically a way of asking a group of qubits a question that tells you whether an error happened, without actually looking at and destroying the fragile quantum information itself. It's one of the core building blocks of quantum error correction. Wait for means this check reads out 4 qubits at once instead of just 2, which is a meaningfully harder and more useful primitive to pull off. The architecture here is called spin shuttling. Instead of wiring every qubit to a fixed neighbor, electrons physically move around the chip to interact with each other, which matters because silicon spin qubits are the modality that looks the most like existing chip manufacturing. If silicon can nail error correction the way superconducting and trapped ion systems already have public roadmaps for, it's the platform with the clearest path to riding the semiconductor industry's existing factories instead of building exotic new ones. Nature's own social accounts, at Nature Asia and at Nature Japan, both posted the release this week, crediting van der Sijpen's team and TU Delft directly. Now, I'll flag this the way I'd flag any single paper. We're going off Nature's own summary here since we haven't seen independent outside write-ups yet, and a peer-reviewed demonstration on one chip is not the same as a scaled-up, useful system. Nobody's claiming spin-shuttling qubits are ready to compete on qubit count today. But primitives like this are exactly the unglamorous steps that eventually add up to error-corrected hardware, so it's worth knowing this exists. Now, sticking with government money and quantum, South Korea's government has formally named quantum computing one of 7 national future industries, under a new plan the Ministry of Science and ICT is calling SEED, with a target of building a domestic 100-qubit error-correcting quantum computer by 2029. That's a policy roadmap, not a delivered machine, and Korea's current hardware base makes that a genuinely hard deadline to hit. But here's the detail that caught my eye. A post from @TechInnovations on X laid out that one of the people advising that National Strategy Committee is Sang-yoon, who runs ID Quantique Korea, an IonQ company. And the same post notes IonQ has been shipping 5th-generation hardware subsystems to the Korean Supercomputing Center KISTI, with assembly happening on site. So the policy announcement is new. The hardware relationship underneath it, per that post, is not. Worth remembering as Korea's plan plays out over the next several years. Next, D-Wave has picked up funding from Canada's National Research Council, up to $300,000 Canadian dollars, to build better software for its Advantage 2 annealing quantum computers. This one's a single-source item straight from D-Wave's own press release, so we haven't independently confirmed the numbers beyond that. The money's going toward new graph minor embedding algorithms, basically the math that maps a real-world optimization problem, like a delivery schedule or a warehouse floor plan, onto the physical layout of D-Wave's Zephyr chip topology. And those algorithms will get folded into the company's open-source Ocean toolkit. D-Wave says the goal is tackling bigger, messier optimization problems across logistics, manufacturing, scheduling, resource allocation, machine learning, and scientific simulation. Chief Development Officer Trevor Lanting framed it as strengthening, in his words, Canada's world-class quantum ecosystem. It's a modest grant in dollar terms, but it's a reminder that annealing, D-Wave's optimization-focused approach that skips the gate model circuit model entirely, still has its own government-funded lane, even while gate model systems from Quantinuum and IBM soak up most of the headlines. And last in the headlines, Yonsei University in South Korea says it will install IBM's newest processor, Nighthawk, this November, making it only the 2nd site in the world to run one, after IBM's own facility in Miami. Nighthawk is the follow-up to IBM's Eagle chip, and the upgrade is about connectivity. Yonsei's director, Young-jae Ho, explained that on Eagle, each qubit averaged just 2.5 connections to its neighbors, so getting information between distant qubits meant extra swap operations that piled up errors along the way. Nighthawk wires each qubit directly to 4 neighbors in a lattice, cutting out a lot of those swaps. Jung says that gets you about 40% more computation at the same error rate. We've noted before that IBM's whole strategy leans hard on quantum paying off as a business, and whether the market's actually buying that long-term is still an open question. This doesn't answer it, but it does show IBM's hardware landing in more labs, this time paired with a new platform called QBridge, aimed at getting industrial users actually using it. Which, speaking of getting quantum hardware into real infrastructure, that's exactly the tension in today's main story. Our main story today, and I'm calling this one the infrastructure test. Quantinuum and Oracle just signed a multi-year deal to put Quantinuum's Helios quantum computer physically inside a US Oracle Cloud infrastructure data center, sitting in the same building as Oracle's GPU and high-performance computing racks as a managed cloud service. And the question worth sitting with is whether that's the moment enterprise quantum stops being a science project you visit and starts being infrastructure you simply rent, the way you'd rent compute or storage today, or whether it's just quantum finding better real estate while the hardware itself still has to clear a usefulness bar. Let's get the facts straight first. Helios is Quantinuum's third-generation trapped ion system. Trapped ion meaning it holds individual charged atoms in place with electric fields and controls them with lasers, as opposed to the superconducting circuit approach IBM and Google use. It runs 98 physical qubits and has demonstrated 48 logical qubits. Logical qubits being the error-corrected, more reliable qubits you build by combining many physical ones, with an average 2-qubit gate fidelity of 99.921%. That clears the so-called 3 nines threshold the industry treats as a meaningful accuracy benchmark, and it draws around 60 kilowatts of power, not counting cooling. This is the same machine Quantinuum commercially launched back in November of 2025, and it comes right on the heels of the company's first earnings report since going public, where revenue was up 279%, a quarter we covered on the show earlier this week. So this deal reads less like a surprise and more like a company converting a strong quarter directly into distribution through one of the biggest cloud platforms on the planet. Here's what's actually changing for a customer. Right now, if you want to run something on Helios, you're generally going through Quantinuum's own cloud access. Under this deal, Oracle Cloud Infrastructure customers will eventually be able to reach Helios the same way they reach Oracle's GPU and HPC resources. Same governance, same identity and access controls, same data services, instead of standing up a separate relationship with a quantum vendor. Oracle says this will be its first quantum computer deployed anywhere in its cloud. But, and this is the important caveat, there's no pricing, no service level agreement, and no firm launch date attached to any of this yet. Oracle's language is that the OCI quantum service will preview sometime in the coming months. So what we have today is a signed agreement and a stated intention, not a live product you can go buy access to this afternoon. The pitch here isn't just proximity, it's hybrid workloads. Quantinuum and Oracle say they're targeting drug discovery, materials science, financial modeling, and large-scale optimization, the kind of problems where you'd want quantum and classical computing working the same pipeline instead of shipping data back and forth between two separate providers. Quantinuum's also pointing to power draw as a selling point, saying a single Helios system uses less than 1% of the electricity of a leading supercomputer for the problems it's suited to. Worth noting, since suited to is doing a lot of work in that sentence, given how narrow the class of provably useful quantum problems still is today. So who's actually excited about this and why? Quantinuum CEO Dr. Rajiv Hazra framed it in the announcement this way. We believe the next phase of enterprise computing will be shaped by bringing quantum, AI, and high-performance computing together. That's the thesis of the whole deal in one sentence. Quantum doesn't compete with the AI data center, it moves into it. On Oracle's side, Mahesh Thiagarajan, who runs Oracle Cloud Infrastructure, made basically the same pitch from the other direction. AI has changed what organizations can imagine, and we believe quantum computing can expand what they're able to solve. He added that the goal is giving developers a practical and secure way to explore how quantum computing could complement their existing AI and HPC workloads. Notice the verb there, explore, not replace. Nobody at Oracle is claiming Helios is about to outrun a GPU cluster on the workloads those clusters are already good at. The more interesting voice to me is Johannes Blaschke, who heads scientific computing at the Ellison Institute of Technology. His argument is that quantum processing units are worth having in the same building as GPUs, specifically because they're a genuinely different kind of hardware. not a faster version of the same thing. And having both under one roof, with one set of tools, lets researchers spend their time on the actual science instead of wrangling infrastructure. And Heather West, who leads quantum research at IDC, made the case that as quantum edges toward enterprise adoption, simplifying access is becoming just as important as improving the chips themselves. Deploying quantum systems within private cloud environments enables organizations to integrate quantum computing into existing AI and HPC workflows through familiar cloud infrastructure and development tools, reducing barriers to adoption. All four of those voices are making the same underlying bet, that the thing holding enterprise quantum back isn't just fidelity numbers, it's friction. Separate accounts, separate compliance reviews, separate procurement conversations. Put the quantum computer inside the cloud enterprises already trust, and some of that friction disappears. Now here's my problem with taking that at full value today. Every specific number in this story, the 98 qubits, the 48 logical qubits, the 99.921% fidelity, is Quantinuum's own figure from Quantinuum's own announcement, and there's no pricing, no SLA, and no launch date to go with any of it. Preview in the coming months is doing the work a ship date should be doing. And we've been here before with this company specifically. Quantinuum has a pattern of re-announcing milestones, like it's non-abelian anyone work, incrementally over a couple of years, without a clean answer on how those results scale past the qubit counts they were demonstrated on. This deal doesn't repeat that pattern. It's not a new physics claim, it's a distribution deal. So it doesn't make that older skepticism worse, but it also doesn't resolve it. Getting Helios into an Oracle data center tells you Quantinuum can sell channel access to a top 3 hyperscaler off the back of a strong earnings quarter. It doesn't tell you Helios is dramatically more useful than it was last month. So where does this land? I think this is a real, structurally important move. Hyperscalers deciding quantum belongs in the same rack row as GPUs is a meaningfully different signal than another university procurement announcement. And it's also, right now, entirely a bet on the come. The infrastructure is being built before the workload that justifies it has been proven at scale. Time for the hype check. I'm putting this one at a 6 out of 10 on substance. The hardware is real, the fidelity numbers clear a genuine industry benchmark, and the distribution logic, quantum writing into enterprises through a cloud platform they already use, is sound. But there's no price, no SLA, and no launch date, and the headline specs are entirely the vendor's own. Call me back when OCI's quantum preview actually has a price tag. If Oracle's quantum preview actually launches with a public price sheet in the next few months, that tells us this crossed from press release to product. If it slips past year's end with still no pricing, that tells us the infrastructure framing was ahead of the reality. Either way, we'll be checking. If today's mix of policy bets, chip upgrades, and cloud deals got you thinking about where this industry's actually headed, follow Quickly Quantum wherever you listen, so tomorrow's episode finds you automatically. This has been Quickly Quantum, an AI-voiced podcast created and built by a real human using today's cutting-edge technology. Nothing you heard on this show is financial advice. I'm Brian Lampert, and I'll catch you all tomorrow. Take care.